Covering over 1 million square feet, the Starfactory is designed with a singular, massive goal: to build up to 365 Starships every single year. That equates to one new rocket rolling off the line every day. This is NASA's Artemis Space Launch System. To construct a vehicle of this size, Legacy Aerospace relies on a sprawling global supply chain. Different contractors across the US and Europe build separate segments, load them onto cargo planes or barges, and slowly bring them together over a period of years to stack a single rocket. Even the traditional factory model fails to meet the speed required by SpaceX. Look at this early automotive line. Henry Ford popularized the standard of sending a central chassis down a single linear conveyor belt, while workers added parts along the way. That works well for a car, but it creates a massive bottleneck for a spacecraft. A geographically dispersed supply chain puts a hard cap on how many rockets can reach orbit in a given year. If the goal is a permanent human presence on Mars, a system that takes 4 years to build just 2 rockets creates a structural limit that the legacy models simply can't solve. To colonize space, SpaceX realized they had to completely scrap the century-old assembly line model. They needed to design an entirely new way to build machines. Tesla's automotive engineers developed a strategy called the unboxed method, a concept adapted for the Starfactory and rebranded as linear adjacent flow. Instead of treating a rocket like a single empty box that slowly moves down a track to get filled with parts, linear adjacent flow breaks the vehicle down into discrete, manageable chunks. The nose, the middle payload section, and the bottom engine bay are all built in completely separate production stations at the exact same time. While one crew is running wires in the nose cone, a completely different team is installing fuel tanks in the middle segment. They never step on each other's toes, and they never have to wait for the previous step to finish. Working in parallel tracks acts as a multiplier on production speed. Instead of a sequential timeline spanning months, an entire rocket takes shape all at once in a matter of days. Every part of that parallel process starts with massive rolls of custom stainless steel. The material you see here is 4 millimeters thick, specifically formulated by SpaceX to handle severe thermal demands. It actually reaches its maximum strength under the extreme freezing temperatures of cryogenic liquid fuel. Over on the first production track, crews begin shaping the top nose cone. Flat steel enters a mold and is subjected to hydroforming. Using 36,000 pounds per square inch of liquid pressure, double what you'd experience at the ocean's bottom, the metal violently bows into its aerodynamic shape. Once welded together, automated robotic arms spot the exterior with imper pins. Those pins lock in thousands of black ceramic hexagons produced in the factory's automated tile bakery, creating the heat shield needed to survive atmospheric re-entry. While the outside gets protected, technicians climb into the unattached nose cone to install header tanks. These are smaller internal fuel reserves used exclusively for the final landing burn, completely plumbed and wired directly on the factory floor. By completing this complex tile work and internal plumbing while the segment is sitting low to the ground and easily accessible, crews avoid the friction of dragging tools and materials up into a cramped, fully assembled rocket. Directly adjacent to that, a second operation is well underway. Flat rolls of steel are welded into giant rings, which are then stacked vertically to form the middle section of the ship, the payload bay. Here, crews cut a long vertical slot into the steel wall to create a payload door. Inside, they construct a tall mechanical rack designed to hold dozens of Starlink satellites. The mechanism functions exactly like a giant Pez dispenser, ejecting payloads one by one into orbit. Because this factory doesn't use a central conveyor belt, all of these massive chunks move through an overhead grid of steel beams. Cranes lift completed segments high into the air and drop them onto rotating stands. The workers can stand completely still while the massive 9-meter-wide steel rings slowly spin directly in front of their tools. The only major operation missing from this roof is engine manufacturing. The highly complex Raptor engines are assembled in California, shipped to Texas for live fire stress testing, and finally brought to the Starfactory for installation. Aside from the massive engines, everything else is centralized under one roof. By relying on overhead cranes and rotating work stands, SpaceX brings the task directly to the technician, cutting out transit delays that plague traditional manufacturing. Eventually, all of these independent adjacent flows have to meet. They converge at a single massive 116-meter-tall structure attached to the end of the factory, the Gigabay. This facility provides 46 million cubic feet of internal volume. If we look at this archival photo of NASA's historic vertical assembly building, originally designed to hold 4 Saturn V moon rockets simultaneously, we get a sense of the scale required here. The Gigabay surpasses it, possessing enough stations to assemble 12 fully stacked Starships and super heavy boosters at the exact same time. Inside, overhead cranes grab the completed nose cone, payload bay, and lower engine segment, stacking them into a single tower. Work crews stationed across multiple vertical levels immediately get to work, tying the separate plumbing, electrical, and gas lines together into one continuous system. The Gigabay acts as the physical crash point for all the parallel tracks. It is the final node where disconnected steel rings and unboxed subassemblies are fully integrated into a functional spacecraft. Speed at this level is dictated by the mission. To deploy the next generation of Starlink satellites and to execute lunar and Martian missions, which demand multiple refueling flights just to support a single landing, SpaceX needs massive volume. A truly reusable architecture means ships will spend days or weeks in orbit, or months in transit to Mars. To maintain a daily launch cadence while active ships are away or undergoing maintenance, you need a deep, rotating inventory of vehicles at various stages of flight readiness. Take a look at this completed Starship prototype on the pad. Establishing a multi-planetary footprint requires hundreds of these vehicles working in tandem. Reaching that volume is strictly a numbers game, demanding an industrial output that aerospace has never seen before. Building one rocket every single day requires a complete departure from legacy manufacturing models. The Starfactory operates as a continuous mass production pipeline, entirely engineered to build the infrastructure of an orbital economy.